Alright, this is day one of probability. Plan for today is going to run through this PowerPoint. This PowerPoint will be posted in Google Classroom. So the probability definition that your book uses: if an event E has n of E equally likely outcomes and its sample space S has n of S equally likely outcomes, the probability of event E is, okay, the P with the E on the inside means the probability of that event. That n of E means the number of ways that can occur. And then the n of S, the sample space, refers to all possibilities. So whatever you're interested in getting a probability of, the number of ways that occurs is the top of the fraction. The total possible number of outcomes is the bottom of the fraction. For any event E, the probability will lie between 0 or 1. So any probability answer you get has to be at the lower bound of 0, upper bound of 1. 0 means the event is impossible to happen. 1 means it's certain to happen. And then everything else is the stuff in the middle. In general, probabilities may be expressed as fractions, decimals, or percents. If there's not a form specified in the instructions, it's your call in terms of how to answer it. As always, with anything else we do in this class, if the instructions specify the answer should be written in a certain form, then write it in that certain form. And in the last feature of probability from this particular slide, the sum of the probabilities in any given experiment is always 1. So sometimes what is easier in certain problems is to figure out, well, what's the probability of something not happening, and then subtracting that from 1, rather than directly figuring out what the probability is of whatever that event. A classic probability question involves what happens if you roll 2 standard fair 6-sided dice. Well, fundamental counting principle tells us that there's going to be 36 possible outcomes. There are 6 ways for the first one to land, 6 ways for the second one to land. 6 times 6 is 36. Now, there's no law that says that when you roll 2 dice, you have to add the numbers that occur on each, but that's typically what is the common probability question. So, for example, of the 36 possibilities, there are only 2 ways you could possibly roll a sum of a 3. So there is a 2 out of 36 chance of rolling a sum of a 3. If you take 2 standard die, roll them, sum their faces. So the smallest sum possible is a 2. You have a 1 out of 36 chance of that occurring. Biggest possibility, biggest sum rather, is a 12. You have a 1 out of 36 chance of that occurring. What's most likely to occur is rolling a 7. The sum of a 7 has a 6 out of 36 chance of occurring. Alright, some questions here. The probability that your sum is less than 4. When it comes to inequalities, you want to make sure that you're careful to make sure you identify whether or not endpoints are included or not. And what I mean by that is less than 4 doesn't include 4. So the sums that are less than 4 are represented by those 3 boxes right there. 3 out of 36 chance of that occurring. Okay, sum is less than 11. Well, less than 11 would be the 10, 9, 8, blah, 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 all the way down to the 2. Now, this is one of those situations where it might be easier to use the fact that we know all the probabilities have to sum to 1. So, figuring out 11 or more is a 3 out of 36 chance. That means everything else would be a 33 out of 36 chance. So rather than counting up the 33 boxes that represent what we're trying to find a probability of, it's easier to count the 3 and then subtract from the total of 36 out of 36. Alright, the next 4 questions kind of go together as a set here. What's the probability that your sum is a multiple of 2? So what I'm going to do is I'm going to circle in blue all the sums that are multiples of 2. Count those up, there's 18 of them. There's an 18 out of 36 chance that the sum you get is a multiple of 2. Okay, part D, what's the probability it's a multiple of 3? So what I'm going to do is circle all the multiples of 3 in red. If you count all those up, there's a total of 12. So there's a 12 out of 36 chance that your sum is a multiple of 3. All right, now blending those guys together. Part E, what's the probability the sum is a multiple of both 2 and 3? Okay, that means it has to have both of them true at the same time anytime you have an AND. So in terms of what we've already done to this particular picture, 1, 2, 3, 4, 5, there's 6 numbers that got both a red circle and a blue circle. So there's a 6 out of 36 chance that that sum you get is both a multiple of 2 and a multiple of 3 at the same time. Alright, last one from this slide. What's the probability it's a multiple of 2 or a multiple of 3? So this means it could be a blue circle, it could be a red circle, or it could be both. When you're doing OR in the probability world, it doesn't mean that they have to be mutually exclusive from each other. It can still be both. So if you count up all the numbers that have either a red or a blue circle, or both, there are 24 of them that are there, so there's a 24 out of 36 chance that you get a sum that's both a multiple of 2 or 3 at the same time. Now for this particular problem, we have a sample space, meaning we have all possible outcomes being shown to us. So we can answer these questions just by visual inspection. Well, you don't always have a sample space, either because it's too complicated or too large in order to produce. And we need to know some probability rules that will allow us to get some answers without necessarily seeing that sample space. So one of our rules has to do with AND and OR. So if you have two events that are mutually exclusive, that means they can't both happen at the same time, and you want to find a probability that A or B occurs. Well, here is the probability of A plus the probability of B. You're going to add those two individual probabilities together. Now it's possible that the A and the B are not mutually exclusive, meaning they share something in common. So the rule for this is you're going to add up the two individual probabilities, and then you're going to subtract off the AND, or what they share in common. So going back up to the problem on the previous slide, for the sum being a multiple of both 2 or 3, another way we could have approached that, if we've already figured out the stuff that came before it, we know that there are 18 ways to get a multiple of 2, 12 ways to get a multiple of 3. Well, the 18 plus the 12 is 30, but some of those guys got counted twice. So then you take away how many got counted twice, which is the 6, and that's the alternate way to get to the 24 without necessarily counting blue and red circles on our sample space. All right. Next scenario we're moving to is dealing with a standard deck of cards. All right, you need to be familiar with what's in a deck of cards. Some basics. There are 52 cards. A standard deck does not include jokers. Half of them are red, and half of them are black. The red suits are the hearts and the diamonds. The black suits are the spades and the clubs. Each suit consists of 13 cards, an ace, a 2 through a 10, and then Jack, Queen, King. Jack, Queen, Kings are known as face cards because they have pictures that include faces on them. So taking that OR scenario into, or that OR rule into the scenario of choosing cards. For this slide, suppose a card is selected randomly from an ordinary deck of 52 playing cards. what is the probability that the card selected is either a spade or a face card? Well, the probability of being a spade is 13 out of 52. There's 13 of each one of the suits. The probability of being a face card is 12 out of 52. The Jack, Queen, King of each one of your 4 suits. So, 13 plus the 12 is 25. If they were mutually exclusive, then your final answer would be 25 out of 52. But if they share something in common, then you have to subtract off what is the and category or the both. So, there are 3 cards that are both spades and face cards at the same time. The Jack, Queen, King of spades fit both categories. So we have to subtract off that 3 out of 52, and for this particular slide, they put the final answer into decimal form. Again, make sure you follow the instructions. If there are no instructions, it's your call on how to express the final answer. All right, some more practice with the cards using these rules. One card is randomly chosen from a standard deck of 52 cards. Find each of the following. A red and a 5. Well, of the 52 cards in the deck, 2 of them are both those categories at the same time. The 5 of diamonds and the 5 of hearts. Red or 5. Well, there are 26 red cards, half the deck, plus 4 5s, and then take away what got counted twice. 28 out of 52 chance that you pick a card that's a red or a 5. Okay, king and a club. There's only one card that fits both those categories at the same time. It's the king of clubs. Okay, king or a club. There are 4 kings in the deck. There are 13 clubs. If they were mutually exclusive, you would add those together and the question would be done. But they're not. It's possible to be both at the same time. You have to subtract off what got counted twice. Okay, last example. The probability you pick one card at random, and that card is both a jack and an ace at the same time. Well, there is no card in the deck that fits both those categories at the same time. That's an impossible event. It's a 0 out of 52 chance of that occurring. Jack or an ace. Well, there are 4 jacks. There are 4 aces. They're mutually exclusive, so we don't have to subtract anything off. The final answer is just the sum of those 2 numbers. I put in at 0 out of 52 just to emphasize if there was something to subtract off, you would do it. But since they're mutually exclusive, there is no extra step. All right, next slide, I'm not going to actually go through this in terms of describing it. It's just more practice, except in a generic sense. We have a list of 20 numbers we're choosing from, and we have the and or questions mixed in. It's the same mathematically as whether we're rolling the dice or choosing the cards. It's just a little bit more practice if you want some more examples to look at. What I do want to do is move on to the next thing, which is our next set of rules. Independent versus dependent events. And we're going to take a little bit of a simplistic view with this, as opposed to those of you that either had or are taking AP statistics. This is a pretty big topic in AP statistics, and it's addressed in a lot more detail. We're going to be looking at some just basic scenarios that involve independent versus dependent for this particular class. 2 events, A and B, are independent if the fact that A occurs has no effect on the probability that B occurs. When 2 events are independent, the probability of both occurring is, and what you do is multiply those 2 individual probabilities together. Okay, in contrast, 2 events, A and B, are dependent if the outcome of A has some effect on the probability of B occurring. When the 2 events are dependent, then the probability of both occurring. Okay, we're still using multiplication as our operation here, but if this affects that, this second probability needs to be adjusted based on what occurred in that event A. Now, as I said previously to starting this slide, there are some rather complicated compared to what we know in this class, scenarios that exist in the probability world. We're going to be looking at just the basic idea of choosing with or without replacement. That's the main scenario we're going to be focusing on for what we do in this class. So for this set of examples here, we have 3 jars. Jar 1 has a grand total of 10 marbles with that color breakdown. Jar 2 has a grand total of 8 with that color breakdown. 3 has 6 with that color breakdown. So for example 1 on this slide, 2 marbles are randomly drawn from jar 1 with replacement. Find blue, white. Okay, that means with replacement means that we're going to take the first marble. After we identify what it is, it goes back in, and then we choose the second one. This notation means that the first one was blue, second one was white. Well, jar 1 has a grand total of 10 marbles. The probability of picking a blue one is 4 out of 10. Now, if that blue marble that we chose goes back into the jar before we pick the second one, then these 2 events are independent. What we picked the first time has no impact on what gets picked the second time. It's the same 10 marbles we're choosing from. We're interested in the second one being white. So, do we have a typo here? Yes, we do. That would be a 2. So that would be an 8 out of 10. Okay, number 2. 2 marbles are randomly drawn one at a time from jar 1 without replacement. Find the probability of blue, white. So same jar, same color combination we're interested in, except for we're doing this without replacement. So that means after we pick the first marble, it doesn't go back in before we choose the second one. So the first pick affects the second pick, or these events are dependent. So for the first pick, we have a 4 out of 10 chance of picking the blue one. Now for the white pick, that bottom of the fraction is correct, but same typo up top here. 2 out of 9 chance of picking the second marble and having it be white. So we have an 8 out of 100 versus an 8 out of 90 chance of choosing from the same jar, same number combination, the with without replacement. All right, next 2 pair up in a similar way. This time we're choosing from, pointing at the wrong thing. We're choosing from jar 2, and we're interested in the probability of getting black, black with replacement, without replacement. So for jar 2, 4 of the 8 marbles are black. If it's with replacement, that means that that first marble goes back in. What happens the first time has no impact on what happens the second time. Those events are independent. We're just multiplying those probabilities as is. We get a 16 out of 64 chance of picking black, black from jar 2 with replacement. Okay, without replacement, first fraction is the same. But now for the second fraction, there's 1 less marble to choose from. So the bottom of the fraction is 7. And there's also 1 less black to choose from. So it's a 4 out of 8 times a 3 out of 7, or a 12 out of 56 chance of getting black, black without replacement. And it looks like we have some typos here on the last one as well. So this can be extended beyond just 2 choices. So the last example is, well, what if there's 3? So 3 marbles are randomly drawn one at a time from jar 3 without replacement. So jar 3 has 6 marbles, 2 gold, 2 silver, 2 brass, and we're interested in the first one being silver, second one being brass, third one being gold. So for the first pick, you have a 2 out of 6 chance of getting a silver marble. There are 5 marbles left now to choose from. Since the first one was silver, both brass are there to pick from. So times a 2 out of 5 for the second fraction. Write that like this. And then gold for the third pick. Now there are 4 marbles left to choose from, because 2 were removed. Without replacement means you don't go back. If the first one was silver and the second one is brass, that means both gold are still there. So for this one here, we have 2 times 2 times 2 is 8 for the top of the fraction. And then 6 times 5 is 30, so 120, so that actual answer was correct. The typos were just in here with those fractions. Alright, last slide. Let's put this in the context of choosing cards. So our prompt up top here is 2 cards are randomly chosen one at a time from a standard deck of 52 cards. The first card is not replaced before the second one is chosen. Find each of the following probabilities. So with replacement, our events are independent, which means we can just multiply the 2 probabilities as is. Without replacement means we have dependent events. That means we have to adjust the second probability based on what happened in the first one. So number 1, both cards are face cards. Well, 12 of the 52 cards are face cards. If it was without replacement, that means for the second pick, there are 51 to choose from. Since the first one was a face card, of those 51 that are left, only 11 of them are face cards. Multiply the fractions, get your answer. Okay, number 2, the first card is an ace. The second card is not an ace. So the bottoms of the fractions are going to be the same. It's going to be the 52, 51. First one, with or without replacement, doesn't matter. Second one, if it's without replacement, there's 1 less card to pick from. So first card being an ace, there are 4 aces in the deck. If the first one we chose as an ace, that means all the not aces still remain. So the 48 cards that are not aces are still in the deck. And then those 2 get multiplied together. Okay, both cards are diamonds, 13 of each suit, so we have a 13 out of 52 chance of the first one being a diamond. 1 less to choose from, 1 less diamond, multiply those together. Number 4, the first card is black and the second card is red. Well, half the deck, 26 out of 52, is black. 1 less card to pick from. If the first one we chose was black, that means all 26 red cards are there to choose from for the second pick. Then multiply those fractions. Last one. The first card is a club, 13 out of 52 chance. The second card is black. Well, 1 less card to choose from. Since a club is a black card, there's 1 less black card from the total of 26. So we have 13 out of 52 times 25 out of 51, and then get our final answer.